So last time we defined the second quantized expressions for, two particle interactions, namely Coulomb interactions. And today we will study in more details Coulomb interactions in momentum space. And then we can actually combine the kinetic energy and potential energy of fermion, electronic systems, for example, in metals. And then the way that we do this is by so-called the Hartree-Fock approach. Okay, so we will, introduce this Hartree-Fock method. First of all, let's start from the very beginning, the two-body interactions by Coulomb. Suppose that these Coulomb interactions are between almost free electrons. Suppose these electrons in the metals are almost free, and they interact by Coulomb, and we consider this as just very weak interactions. And then the second quantized form for this Coulomb interactions is given by this kind of a four operator, two creation and two destruction operator that we defined earlier. In particular, we try to represent such Coulomb interactions in momentum space, so that those, remember the previous indices are I, J, K, L, something like that. But this I, J, K, L could be any indices in any, orthonormal eigenbasis. But here, since all these electrons are almost free, and we can take this orthonormal basis as the K space, representation of free electron plane wave. So such is the eigenbasis for free electron plane wave. Okay, so we could expand this operator in terms of such momentum eigenstates. And then we can label them as K, K prime, K double prime, K triple prime. And in general, those four momentum could be different. And as a result, this matrix element, this V I, J, K, L, or V, K, K prime, K double prime, K triple prime, represents this scattering between two electrons by Coulomb. Remember that. So there are two initial states, K and K prime, and two final states, K double prime and K triple prime, right? And this matrix element of this momentum indices is given by this type of Fourier integral, because we are working in the momentum eigenbasis. As a result, those expansion coefficients, nothing but Fourier exponentials. So for this K and K prime, we get minus I exponents K dot R1 or K prime dot R2. And for the other, final states exponents, the exponents are plus I K double prime dot R2 and K triple prime dot R1. So then we could just combine this exponentials with the same, vector R1 or R2, so that this four exponentials become two exponential vectors. Remember, the potential term is the function between these two vectors, R1 and R2. And then we could further Fourier transform this potential term, because this potential energy or potential term is a function of R. Of course, R is the distance between R1 and R2. But since this is just some arbitrary function mathematically, so you could imagine that I could Fourier transform this, from the real space representation to the momentum space representation of the Coulomb potential. And so in Q space or K space, this is the Fourier sum of this VR. So we got V of Q, which is the K-space representation of the Coulomb potential, and the Fourier coefficients, e to the iq dot r1 minus r2, right? So this is nothing but the Fourier transform for V R1 minus R2. So we transformed everything in K-space form. The reason will become clear. So now let's just combine everything. So when we combine, right, so this is K, this should be, sorry. So this is the case. R1 should be K triple prime minus K, and R2 should be double prime minus K prime. Is that so? Okay, sorry about that. So, yeah. So, R1 triple prime is K, R2 double prime minus K. All right? Okay. So now you could perform this Fourier integral to get rid of these exponential factors, because if you could just integrate the R1 and the R2 independently. So these two integrals could be separated, and when you evaluate this integral, you get the Dirac delta function, right? So this is, so of course, you should just give this volume factor 1 each for this double integral, and after this real space integral, you get delta function. So now let's just plug in this matrix element back to this Fourier integral of this Coulomb potential. So V hat is given by sum over Q and another 4 momentum sum, V of Q, delta K is K plus Q, and delta K prime minus Q. So we have 5 summations, 4 Ks and 1 Q, and but we have 2 delta functions. And so we can get rid of these 2 delta functions, and equivalently we remove 2 summations out of the 5, right? So we could take advantage of this Dirac delta function. So this summation is 0 unless the argument in the Dirac delta function vanishes. And likewise, we should satisfy these 2 conditions. All right, so let's remove this summation over K double prime and K triple prime, because K triple prime is K minus Q, and K double prime is K prime plus Q. All right, so therefore we could get rid of this 2 by substituting these identities. And we could simplify this K prime and Q, V of Q, C dagger K plus Q, and C dagger K prime minus Q, CK prime and CK. It's either way. So you could plug in this K double prime, K triple prime here, but you could simply just relabel this K and Q so that this is this expression, but there's an equivalent expression. Say if I remove K and K prime summation, I get K double prime, K triple prime, V of Q, C dagger K triple prime plus Q, C dagger double prime minus Q, CK prime, CK triple prime. All right, so there's a degrees of freedom to choose which 2 momentum variables that you want to remove, right? So you could remove either k and k prime or k double prime, k triple prime. It's your choice. So that I could simply just relabel this k and k prime and k double prime, k triple prime, so that this, say, k triple prime is actually the same as k, and k double prime is actually k prime. And this, right? So I could relabel this indices as I like. So I can call this k, k double prime, and k prime, k triple prime. Whatever the indices I call, I have a freedom to do so, right? So, but you need to really interchange those indices in a consistent way. And so these two expressions are identical. To actually more convenient, for our convenience, we could simply choose this expression with just k and k prime, because there are many double prime, triple prime, so it's a bit complicated. So we could simply just use this simple form. And diagrammatically, we could express again the scattering between two electrons. So there are two incoming electrons carry momentum k and k prime, and after this Coulomb scattering, there is a momentum transfer q in between these two electron states, and so that the scattered state for this corresponding to this initial state k becomes k plus q, and for this k prime initial state, now the scattered state becomes k prime minus q, because the momentum should be conserved either here or there, so that k plus q is actually k plus q. And if there's a momentum given away, so from this k prime, so the resulting momentum should be k prime minus q. So let me just draw it in a cleaner way. So this is k prime. All right? Okay, so that's the Coulomb interactions momentum space. So you got two incoming electrons carry k and k prime momentum, and they exchange momentum q. Later we will specify what this q could be, and then one of this electron carry momentum q more, and another carry momentum q less. So that's the Coulomb interaction. So let's take a short break. When we come back, we will continue to really evaluate this Fourier integral of V of q for the Coulomb interactions. Okay, so let's take a short break. So now let's really explicitly calculate the Fourier transform of this V of r in momentum space, which is V of q. And we know that this is Coulomb energy between two electrons, which is given by E squared over the distance between these two. And V of q is just this Fourier integral in three-dimensional space, which is given by this kind of a spherical coordinate representation of the integration. Okay, so you could integrate over the r by going into the spherical coordinate. Okay, so there's a theta, and in between this momentum q and r, suppose this is r and this is q, right? Okay, and this Coulomb interaction shows spherical symmetry, right? So because it only depends on this distance r, ri minus rj, and so you get this the r, which you could really change your integration variables to actually integrate only the relative distance vector between these two, r and rj. So there is an angle between little q and r, which I call the theta, And you could just expand this exponents in the exponential factor and also using the spherical coordinate for the three-dimensional integration over the relative distance vector dr. So there's a 2 pi r squared, which is the say when you change this d3r, you get this 2 pi r squared dr. Of course, there is a d cosine theta right here, and there's one of r's from this Coulomb potential, and that's all. So in the spherical coordinates, it can be simplified as that integration over the r and also the theta. And the cosine theta runs from -1 to 1, which goes from 0 to pi. Okay, so let's just simplify this. And r, the magnitude of this distance vector r runs from 0 to infinity, and the cosine theta runs from -1 to +1, and e to the I q r cosine theta with a minus sign. And there's r. Right? So you cancel this r in the denominator by the r squared in the numerator, so you get vector of r remaining. So I can rewrite this integral in this following form. So 2 pi e squared dr and minus I q e to the minus I q r x, where x cosine theta. So you could rearrange this term so that this r could be inside of the cosine theta. So this is r cosine theta, and e to the minus I q r cosine theta. Okay, so I could just move this r, vector of r, inside of this d cosine theta to make it dr cosine theta. And the reason why I'm doing this because there's a qr cosine theta here. Right? So I could just integrate over the cosine theta or r cosine theta so that I get this. And I can define this x as cosine theta, and after integrating over cosine theta, this is the remaining part of the integration over dr. And so I can just continue with my integration. So this is 2 pi e squared infinity dr minus iq minus iqr minus e to the iqr. Yes? All right? And let me just combine everything. 2 pi e squared over iq dr 0 to infinity e to the iqr minus e to the minus iqr. Okay, so this innocent looking integral shows some problems here, and it is because of this term, which is going to be divergent. Right? So to understand the origin of this divergence, you could simply just change this to say I sine qr, something like that. Okay, so if you try to evaluate this, the r run from 0 to infinity and sine qr, and q is finite in general, and this integration does not converge. Okay, especially when q goes 0. right? So you could check this statement. So we will come back to here later. So as I mentioned, this V is actually proportional to this 1 over R, which is a long-range force. So because of this 1 over R potential, it doesn't vanish in the long distance limit. So there's a long tail. When R goes to very large value, this potential doesn't vanish. Okay, and if you Fourier transform this long-range Coulomb force, and you'll get divergence in the limit of Q goes to 0. So we will come back to this for this correct physical interpretation. What went wrong here? Nothing is wrong here. It's just that this is the nature of long-range force. So later we're going to cut this long-range force at some point here, so that when distance exceeds some critical distance or some crossover scale, then the potentials drops exponentially. And this is what really happens in most metals. You get Coulomb interaction when distance is small, but then it gets screened, so-called screening potential, Coulomb screening. So in realistic metals, Coulomb interactions are not long-range force. Okay, so this is the independent electron model, but in a real, say, solid or metals, the Coulomb interactions are cut short-ranged. It's called the Coulomb screening. Okay, so the Coulomb interaction, the Coulomb potential, is no longer a long-range force in the realistic materials. But here, we simply just consider an ideal case where these Coulomb interactions are long-range. Okay, so that it exists in between, say, any distance between these two electrons at any distance. It could be infinitely long-ranged force, so that even these two electrons are really far apart, so they can feel this Coulomb 1 over R potential. So this is what we are doing here, and we will fix this divergence later. But let's just analyze this divergence first and try to fix this problem artificially. So of course, in this ideal case, this 1 over R potential will cause this divergence, but we could fix this just momentarily by introducing a so-called convergence factor. So we can fix this problem by introducing the convergence factor, so-called delta. So suppose the delta is small and approach to 0, and I could just multiply this Coulomb energy, Coulomb potential, by this e to the minus delta times R, and this is called convergence factor, because when R goes to infinity, this convergence factor is actually cut off this potential, and this potential drops to 0. Okay, so therefore this V of R when R goes to infinity goes to 0. Okay, of course this is just temporarily fixed, so it doesn't fix the whole problem, because unless we really get this screening of Coulomb potential, which we'll discuss later, otherwise this is not the real fix. It's just temporarily we make this quantity non-divergent. So this is responsible for the decay of this Coulomb potential. It's just artificial. Then we use that to recalculate this V of Q, and this time we could avoid this divergence problem. So delta goes to 0, the R I Q plus I delta minus e to the minus I q minus I delta. So by introducing this extra decay factor into this Coulomb potential in real space, and we are able to rewrite this V of q in terms of this q plus I delta and q minus I delta in exponent. Okay, so again, this is just an artificial way to fix this divergence factor, and which allows us to really compute this V of q to the final form. So if you use your knowledge in the complex analysis, you will get this, which is, of course, there's I delta and minus I delta, something like that. So you get 4 pi e squared q squared plus delta squared. All right, so by introducing this convergence factor, we avoid this divergence of this V of q when q goes to 0. So now, when q goes to 0, this becomes 4 pi e squared over delta squared. Of course, delta is actually small, so this doesn't really solve the problem, okay? Because when delta goes 0, this is 1 over delta squared, which is also divergent, okay? But mathematically, this appears convergent, or at least shows a finite value when delta is finite and q goes 0, right? So this shows some finite value when delta finite, but q goes to 0. So this is still finite, slightly better than 4 pi e squared divided by 0 squared. Okay, so but still remember we haven't fixed this problem yet, but we just mathematically pretend that this problem is not there because we introduce the convergence factor, okay, to make it, non-divergent in the presence of finite delta. Okay, so this is the sort of a formal expression for this Coulomb interaction between two electrons in the long-range limit, where this 1 over r potential, extends all the way to infinitely long range. So later we're going to find a way to cut this Coulomb long-range force, and by introducing a finite delta square here to replace this delta, which is infinitesimal. So let's take a short break. When we come back, we will continue analyzing this, divergence of this Coulomb potential, 1 over r potential in Q space, and trying to argue that this divergence is another real divergence, and it does not cause real crisis. So we can actually use the charge neutrality condition to argue that this divergence will be cancelled by other type of Coulomb energy, which is also divergence. Okay, so let's take a short break. Good. So let's discuss the divergence of this V of Q. So V of Q, Q squared plus delta squared, but delta goes to 0. And what does that mean? Okay, so this means that when Q goes 0, this diverges. And this just tells us that suppose we have a bunch of electrons, and without considering the mutual influence of this electron Coulomb interactions on each other, so we consider those electrons just independent electron pair. Suppose they are just independent electron pairs, and this divergence is nothing but telling us that the Coulomb energy of the system in the thermodynamic limit actually is made of infinite independent electron pairs. Okay, so this is nothing but telling us that suppose we consider this V of Q when Q goes 0, is nothing but V of R e to the I Q R dr, right? And Q goes 0. So if we consider this is an inverse Fourier transform, and V of Q when Q goes 0 is nothing but, you put this Q 0 in the exponential factor, and you sum over V of R dr, right? So this is nothing but you sum over your Coulomb potential. So this is nothing but V of R dr. As I mentioned, if V of R is the long range 1 over R potential, and you sum over this V of R dr, you get infinity. So that's the nature of a long range interaction. So if these two electrons, no matter how far away they are, so they still feel this Coulomb potential, if you add up all these Coulomb energies, you should get infinity. So that's for sure. And the reason is that in the thermodynamic limits, the number of electrons goes to infinity. Of course, not infinity, but it's that much, 10 to the 23rd, that many electrons. So this is considered as infinity, right? So if you get that much pairs of independent electrons influenced by the long-range Coulomb interactions, for sure your Coulomb energy will explode. So that's why you get a divergence of the Fourier transform V of Q when Q goes 0. This is nothing but the sum over all the Coulomb potential in real space. And this is nothing but the long-range force, nature of Coulomb force. And of course, if you get infinite number of electron pairs in your system, there should be, of course, infinite number of ions, right? Because in your solids, there are not just free electrons, but ion cores as well. So electrons are distributed in the neighborhood of these ion cores. So that's the more realistic pictures of your metals or solids. And so if you just consider the Coulomb energy between any pairs of free electrons, and you get infinity, but you should also calculate the potential between ions, right? Because the Coulomb interactions are everywhere, so it is between any two electrons. It is also between two ions, and of course, it is between ion and electrons, right? So you got three types of Coulomb interactions in your solids, but each of them, diverges, right? But the signs are different because electron-electron are repulsive and ion-ions are repulsive, but electron-ions interactions are attractive. Okay? So you got bunch of plus infinity and minus infinity, and when you sum up all these Coulomb energies between any charges in your realistic solid state, even if they are long-range interactions, when you sum up, because of charge neutrality, they should all get cancelled. So let me just, this is just V of Q goes to 0, which is infinity between electrons. And you should also get ions with a similar form, which I call this, say, W0 plus, and this is called, remember, this is 1/2 of n times n minus 1 V0. Right? So this is simply just sum of all Coulomb energies between all pairs of electrons, so which is m times n minus 1. That many pairs contribute to this Coulomb energy. And then you get electron ion, which is minus n times V0 plus, where V0 plus is the average positive charge. All right, so you could sum up all these three. You sum up all these three, 1, 2, and 3. you get 0 because of charge neutrality in your metals. And when you sum over all these Coulomb energies between all pairs of charged particles in your solids or in your metals, and you effectively sum of all charged particles. Okay, so this is effective charge, net charge, which is sum over rho plus and rho minus all charged particles. Of course, this vanishes. And of course, we don't need to calculate those, V0, V0 plus, and, W0 plus, and so on. And the reason is that when we sum of all these Coulomb energies, they effectively reduce to the net charge of the system. And because the net charge is actually 0 in ordinary metals, because you get equal number of negative charge and equal number of positive ion charge, right, in your system, so that you get a charge neutral system. So in a way that we don't need to worry about this divergence anymore. Of course, if you separately just calculate electron Coulomb interactions, of course you get the infinity, but if you sum of all other Coulomb interactions in other charges, then you should get cancellations. So that's the temporary solutions of this divergence of your long-range Coulomb energy, but we will fix that later when we study the screening of a Coulomb potential. So let's just summarize the, say, Hamiltonian of a metal, including this electron Coulomb energy. Suppose this Coulomb energy is long range, and of course there's a summation over spin, but for the moment I don't put this spin. This is here, so we will discuss the spin, degrees of freedom later. So, and as I mentioned, there's two almost free electrons come in, and they get Coulomb scattered, and after scattering, they become another 2 electrons. So that's the full Hamiltonian we have for metals in the presence of Coulomb interactions. Okay, so epsilon k is nothing but the free electron energy, which is, say, h bar squared k squared over 2m. So now we pretend that these Coulomb interactions are weak, and we could perform sort of a perturbation based on the Sommerfeld free electron gas, and suppose this is a weak perturbation. And this is what this Hartree-Fock approach is based, where we consider this free electron Sommerfeld gas is the ground state, unperturbed ground state of our metals, and then we put this weak Coulomb potential to perturb such a free electron gas and see the corrections up to second order imperturbation, and we collect those corrections, and we compare this so-called Hartree-Fock energy up to second order imperturbation with the experimental observations. So that's the Hartree-Fock approach, which is called H0, and I call this H interaction. So H0 is the unperturbed ground state plus H interaction, which is a weak perturbation. So later we'll see that this Coulomb interaction in the long-range limit, in the long-range form, is not weak. It is really, really strong, and this Hartree-Fock approach fails, okay, to capture many low-temperature behaviors of metals. Okay, so this approach failed. Okay, so but even though it fails, we need to learn something useful from this, say, failures. Okay, so let's just assume that we could do this Hartree-Fock approximation. And at 0th order, we got a Sommerfeld electron gas, which is the 0th order. I call this H0 is sum over K epsilon K, K which is sum over K, epsilon K and K. Right? So N of K is the occupation number operator, which gives you this eigenvalue delta Kk prime times K prime. Okay, so this is K if K is the same as K prime, but 0 if they are not the same. So we have done that already. So now let's consider n particle free electron state, which is the ground state of unperturbed Hamiltonian H0, which is nothing but the product of all this single creation operator of a free electron, right? So we define that. So this pi represents the product of this all single electron creation operator, okay? So, and those creation operators for fermions satisfy this anti-commutation rules. And this is my starting point, phi. So if I simply just evaluate this many-body ground state energy, I get sum over K, epsilon K, N of K, acting on this phi, which is nothing but sum over K, epsilon K, sum over K prime, delta K, K prime, and phi, which is sum over I from 1 to n, epsilon Ki phi. So of course, this is what we already see here, right? So in the occupation number basis, the eigenenergy is just, single electron connect energy, and the total energy is given by the number of electrons times the kinetic energy per electron. So for the unperturbed system, so the total energy is nothing but this sum over K epsilon K. And we call this Hartree energy, epsilon 0, which is 2.22 Rs squared Rydberg constant per particle. Okay, so for free electron Sommerfeld gas, if you sum over all the free electron kinetic energy, you'll get this value. Okay, so this is your homework. Derive it. So derive this number, 2.21 divided by R squared times Rydberg constant per particle. So, and this number should appear in all textbooks references that I listed. Okay, so you can find this pretty easily, and this is just a review. But this is just unperturbed eigenenergy, total energy. Okay, so now we would like to use this phi, this unperturbed many-body electron state, as a starting point, and we try to perturb this Coulomb interactions. Okay, so let's take a short break. So this is nothing but a repetition of what we have done so far. Okay, but it's good to review, and then we will do something non-trivial. So let's continue. As I mentioned, let's assume that the Sommerfeld electron gas is the 0th order ground state of the weakly Coulomb interacting electron system. And we consider this phi as many-body ground state for the 0th order in perturbation. And this psi is the full exact ground state of this full Hamiltonian. Okay, so this is full Hamiltonian. This is only H0. Now we try to value this eigenenergy, expression value of the Hamiltonian, sandwiched by this full exact many-body ground state, which we don't know. Okay? But within this perturbation theory, this is approximately given by this phi, which is the 0th order ground state, sandwich this Hamiltonian. So this is just approximation in perturbation, and we take this as a reasonable starting point to calculate these corrections due to this potential term. And this is called the Hartree-Fock energy, epsilon HF, which is phi H0 plus V, which is epsilon 0. Epsilon 0 is the ground state energy, kinetic energy of a zeroth order Hamiltonian H0, which is 2.21 divided by R squared times Rydberg constant. And the second term is the non-trivial term we will focus here. So it's the matrix element of this Coulomb interaction term sandwiched by this zeroth order ground state. So that's the non-trivial term. So let's just try to do it. So to evaluate this, so let me just repeat this. And suppose I assign spin here, sigma, sigma prime, and sigma prime, and sigma. And let's just see what are the non-zero contributions that we can get from this matrix element, right? So we should sum over k prime, and q, but we should find the relation between those, say, two initial states and two final states, so that when we sandwich this by this phi, you get non-zero. Okay? So if we don't properly choose this initial and final state, then this matrix element vanishes. Okay? So this is the thing that we need to pay attention to. Right? So in general, we have 4 states, 2 initial, 2 finals, and each of these states, 4 states, is actually a non-interacting, say, single electron state, right? So because this is our basis, so we perturb this, in the basis of the non-perturbed ground state phi, which is the product of the independent free electron wave function, and those initial and final states are nothing but this free electron plane waves, right? So all the states, all this k prime plus q, and k minus q are free electron states. Okay, so you know that this operator C dagger and C will create or destroy a single free electron state. Okay, and these will actually change the number of a free electron in your non-perturbed eigenstate. Okay, phi. Okay, but we have this orthonormal conditions. So this k, say k1, kn, k1 prime, km prime. Suppose this is my phi, and this is my phi prime, where phi and phi prime are nothing but non-interacting many-body ground state, and they should orthogonal to each other. Okay, so because they form orthogonal and normalized eigenbases for the non-perturbed ground state. Okay, and all this momentum, initial and final momentum that we are talking about are nothing but one of those k's in the ground state many-body wave function, but they have the orthogonal normalization conditions, so that we need to make sure that the initial states and final states are the same. So because of orthonormal between phi and phi prime, the initial and final states have to be the same. Okay, so you could check these properties at home, but the message is that remember this k minus q, k prime plus q, and also k prime and k are nothing but one of these momentum states in this many-body wave function of the unperturbed ground state, phi, right? Okay, so that if you destroy this, and you should destroy your many-body ground state wave function, and then if you say create, then you should create that states. So at the end of the day, you should find this matrix element as all these different states in between this broad and cat state, which you could form some kind of a matrix element or the inner product. Okay, because if you wish, so you destroy 2 electrons, k prime and k here, and then if you reversely increase this 2 electrons to the left, you also destroy this 2 single electron wave function in the phi broad state, and then you simply just make this inner product between these 2 states, many body states, and unless this initial and final state are exactly the same, otherwise you get 0. So I understand this because this phi broad state is actually the function of what? K and k prime, right? So k minus q and k prime plus q. And phi prime on the right is a function of k prime and k, right? So you should pair them up either by assigning that k is the same as k minus q and k prime is k prime plus q, like this direct kind of term, or you could exchange this momentum variables like this. So k becomes k prime plus q and k prime becomes k minus q. So there are only 2 possibilities that remain to contribute to this matrix element, but other possibilities would vanish because of also normal properties of this non-perturbed ground state wave function. So you could more rigorously prove this statement that initial and final state have to be the same. So there are only 2 possibilities, and this is because the occupation number is conserved. And this tells us there are only 2 possibilities. By the way, you could check this by simply just expanding this phi in the product of all this, single particle wave function, ck1 dagger, ck2 dagger, and so on, equal 0. Okay, so you could easily verify that the 2 initial states have to be the same as 2 final states, either in a direct sense or in an exchange sense, right? So the 2 possibilities are you get a direct scattering, k to k and k prime to k prime, with the exchange momentum q0, which we call this v0. And so in that sense, k equals k minus q and k prime equals k prime plus q. Suppose I identify the initial state k as a final state k minus q, and k prime to actually k prime plus q, which means that q must be 0 because k is k minus q, so q is 0. And k prime is k prime plus q, so q is 0, right? And that's the first possibility. And the second possibility is the other way around, that you exchange these 2 momentum. So we call this exchange term, k and k prime, and we call this v of q and k prime to k. So k prime is actually k minus q, which is the outgoing particle with respect to this initial particle k, and k becomes k prime plus q, which is the outgoing electron states with respect to the k prime initial state. If you look at this initial and final momentum, you find that they are exchanged, right? So k becomes k prime and k prime becomes k. So they get exchanged, so we call it exchange term. And the first possibility is a direct term because there's no momentum transfer, and this electron state initially said k, and the final state is also k, and k prime is k prime. Okay, so it's called direct term. So the direct term lead to some just a finite or some constant value, which we will evaluate next time. But the exchange term will lead to some non-trivial contributions. Okay, so if you use the diagram to illustrate this kind of interaction, we call this K1 and K2, and there's a wavy line link this two. This wavy line later on will be interpreted as the photon, right? So because the Coulomb interaction is nothing but electromagnetic wave, and in the second quantized formalism, electromagnetic wave is nothing but photon. So two electrons exchange photon with the photon momentum 0 in the direct term, and for the exchange term, you got different situation because now, so this circle represents this Fermi sphere, Fermi surface. So the active electrons are surrounding the Fermi surface, right, as we mentioned. So if one electron near the Fermi surface carry momentum K1, another one carry K2, and they are in a different orientation of the Fermi surface, and they could exchange momentum and get Coulomb scattered, but the direct term, they don't exchange any momentum. Okay, but they simply just interact by Coulomb when Q goes 0, and K1 goes to K1, and K2 goes to K2. But the exchange term tells us that these two electron states get exchanged. So if there are two initial states, K and K prime, and with the help of this wavy line or the photon or Coulomb interactions, K becomes K prime and K prime becomes K. And this is the, say, Fermi momentum. Okay, so we will next time evaluate this exchange energy within the Hartree-Fock formalism. And the way that we calculate is nothing but just transform these four Fermi operators in terms of occupation number operator that we introduced earlier, and we emphasize many times that the advantage of using second quantization expressions for operators is that we are able to perform some calculations. So in the fermionic case, near the Fermi surface, and by transforming all this, this complicated operators in terms of occupation number operators. And we know what these eigenvalues of occupation number operators. They are nothing but either Fermi-Dirac or Bose-Einstein distribution function that we are familiar with. And so the problem reduces to the the extent that we can deal with. Okay, so if we follow the particle and we don't know how to solve this, Schrödinger equation for those many coupled electrons and ions, but if we, count these quasi-particles or electron numbers near the Fermi surface, then it is doable. Okay, because we know the ground state is actually very stable, and they don't participate in this kind of thermal excitations. And the thermal excitations are present only in between this inner and outer shell that we introduced many times in the past. And we could calculate those quasi-particle excitations near the Fermi level at the finite temperature, and based on this perturbation theory. So next time we will finish this calculation. Suppose we know this phi, which is nothing but this unperturbed eigenstate of independent electron wave functions, and we could sort of use our knowledge of anti-computation rules for Fermi operators, and we can show that this is nothing but the function of occupation number operators. Okay, so let me just tell you the final answer. So this exchange term is going to be n k prime n k minus and plus n k. Okay, so So we will do that on Wednesday, right? So we could look at this exchange processes and use this fermion anti-commutation rules and also normal properties of this unperturbed many body ground state, and we can show that this 4 electron operator now reduces to this occupation number operator here. So the goal is to reduce all this complicated fermion or boson operators to this occupation number operators, and we know how to deal with those things. Okay, so and this is the advantage that we use this second quantization formalism. Let me summarize. So we Fourier transform the Coulomb interaction energy, and we find the divergence near Q goes 0, and we know that this divergence is just divergence of this long-range Coulomb energy in this thermodynamic limit where you consider infinite number of particles in there. And then we Fourier transform this Coulomb interaction and also the kinetic energy, and then we take this Hartree-Fock approach by assuming the Sommerfeld free electron gas as starting point on perturbed eigenstate, and we perturb this by introducing this small weak Coulomb term, and we try to evaluate this matrix element. And there are 2 contributions. One is the direct term, and we will compute this direct term next time, and another is exchange term, okay, which gives rise to non-trivial contributions. And later we'll show that this Hartree-Fock approach cannot get reasonable results if you compare their predictions with real experiments. And we will see what went wrong with Hartree-Fock, and we will improve the Hartree-Fock, or we should abandon Hartree-Fock and by introducing more relevant variables. And that more relevant variables is the density fluctuations. And that will lead to the screening of a Coulomb potential. So that's enough for today, and so I'll see you on Wednesday.